Hello, good morning, everyone. We are about to start the third and final day of the second OPENCOASTS E-Tutorial. And just to remind you all that all lectures are recorded, with exception for the question periods. And we just sent a new streaming link to everyone, to every participant. So please follow us, and if you have any questions, you can ask on the chat or interrupt after the lectures. We're about to start now. Thank you. To the third day of the second OPENCOASTS E-Tutorial. My name is Gonçalo Jesus. I'm from National Laboratory for Civil in Portugal. The first day's lectures are available at opencoasts.lenec.pt. This third day is directed to developers training. Today's program includes a front-end presentation in the first half of the day. On the second half, a back-end presentation and a EOSC infrastructures presentation. As a reminder, if you have any question, raise your hand in Zoom and wait for the moderator to give you the stand. Also, you can type your question in the chat directly. We will answer it as soon as possible. Finally, please avoid being late to the sessions and also remain silent during the lessons. In the end, the organizers will be around and will answer any questions if you have. Enjoy the tutorial, and if you have any questions, you have my contact in this slide. Welcome. Hi, my name is Gonçalo Jesus. I'm a researcher from National Laboratory for Civil Engineering, and now I'm going to present you the front-end concept, software, and some implementation steps. First of all, we are aiming this part of the course for system admins, full-stack developers, web developers, designers, back-end specialists, content producers, and everyone else that is interested in customizing the front-end part of OPENCOAST's website. In this presentation, we will discuss the software overview, the front-end structure, and the administration application of front-end. As you know by now, the OPENCOAST front-end website is available at opencoast.ncg.ingrid.pt. Please visit and register if you haven't already. Starting with the software overview, in terms of the front end, we list here the main technologies by which the front end is composed of: Python, HTML, CSS, Bootstrap, JavaScript, which includes jQuery, Django, PostgreSQL, NCWMS as a map server, Leaflet, Geojson, ArcGIS base map layers. We will first characterize the main technologies in order for you to understand how it was built, the front end, and how we can customize it. First, let's talk about Python. Python is a high-level programming language, open source and community-driven. It is cross-platform, it's dynamic typed, it is freely usable even for commercial use. It contains Python objects and classes, modules that help you in building your software, pip, and virtual environments. In order to run and build OPENCOASTs, we make use of two useful tools, pip and virtualenv. Pip is a tool for installing and managing Python packages, similar or an alternative to easy install. Virtualenv is a tool to isolate a Python environment. Regarding pip, it minimizes the problems of searching and finding packages and modules, of confirming the validity of modules. Also, it minimizes the problems of installing packages and modules, and it helps you control the different packages versions and the requirements of packages. Regarding virtualenv, let's discuss the importance of virtual environments. They allow for isolation, where Python packages are controlled in a single environment. They also minimize problems with permissions. There's no need for sudoers. In terms of organization, each project can maintain its own requirements files of Python packages. And finally, we will not have globalization issues. Therefore, we don't need to install packages that may affect the whole system. So, virtualenv minimizes the problems of using different Python versions, testing some packages without ruining the system integrity, delivering Python code to other systems, and verifying applications in other systems. Here you have an example of pip requirements file for OPENCOAST project. You have, of course, Django, that we will discuss next, and you also have PsychoPG, NetCDF, Geojson, and the rest. In this slide, we introduce Django. What is Django? Django is a high-level framework for rapid web development. It follows the model view template design pattern. It offers a complete stack of tools in which data is modeled with Python classes. It also offers a production-ready data admin interface generated dynamically. It offers an elegant system for mapping URLs to Python code, generic views to handle common requests, and it's a clean and powerful template language. Across this presentation, we will discuss thoroughly Django Model View Template Pattern, MVT. Models describe the data we have. Views control what user sees. Template is how users see the information, and controller is what it is called the URL dispatcher. On the right part of the slide, we can see the flow of information starting from a web browser action into the database and returning back to the web browser. Some of you might have already heard about the more common MVC pattern. So let's just compare both patterns. In the common MVC architectures, we have models that deals with the data-related logic, view that are responsible for collecting data from the model or user and presenting it, and here we have the controller that controls the data flow and interaction between view and model. Whereas in an MVT architecture, the model, same as the model in MVC, the view in this MVT design pattern, it decides what data should be displayed, and templates are used to specify a structure for an output, where data can be populated in a template using placeholders. Regarding differences between MVC and MVT patterns, in a model view controller pattern, we have to write all the control-specific code. In an MVT design pattern, the controller part is taken care of by the framework itself. In an MVT architecture, we don't need to write any code related to the fetching data from the database and mapping it to the URL. All these activities are handled by the framework itself. We just tell the framework what data should be presented to the user. On Django models, they are a description of a database layout as a Python class or model. They normally represent one database table. As any database table, it has fields like char field, text field, integer, dates, URL, and many others. In terms of Django views, they are ready-made logic for many common tasks. They can issue a redirect, display a paginated list of objects, display a detailed page for a single object, or more importantly, object creation, updating, and deletion, with or without authorization. In templates, we have text files or HTML files that contain variables, filters, and tags that control the logic of the rendering process. We have here some of those examples. Regarding the other technologies, we have NCWMS as a map server. It provides data visualization over the web. NCWMS is implemented as a Java web application, packaged as a web archive file for deployment in a standard servlet container such as Apache Tomcat. NCWMS uses WMS standards to expose data directly from the netcdf, but it also supports other formats. It offers quick and simple visualization, and it is based on open standards. Also, it is modular, so libraries can be used for other data manipulation and visualization applications, which in our case is Leaflet, the visualization application. Leaflet is a lightweight open source toolkit for displaying maps. It is small and fast. It provides an easy-to-use API, a wide range of plugins, supports mobile devices, and uses HTML5 and CSS3. Also, it is compatible with a wide range of map tile providers, including ArcGIS Maps, OpenStreetMaps, CloudMate, and many others. Finally, to wrap up the software overview, we also use Geojson. Geojson is a geographic version of JSON, and it may represent a geometry, a feature, or a collection of features, supporting points, lines, polygons, multipoints, and many other features. These features contain a geometry object and additional properties. The second part of this presentation is focused on the front-end settings and models. Therefore, we will discuss a bit further the Django MVT pattern, Django structure, including folders and apps, the Django settings, and its models. In previous slides, we presented the MVT pattern, Now we are going to show you how it is used both in terms of the front-end organization and also in terms of the data flow. In Django, every created web app is called a project, and a project is a sum of applications. These apps are also structured according to the MVT pattern, and a project is a collection of configuration and multiple apps, or one app, depending on the project. Here we have the OpenCoast project layout. We have a project root that includes a manage.py file and a project OpenCoasts folder, among the other apps folders that are going to be presented in the following slides. Also, in Proj OpenCoasts folder, we have the settings.py, urls.py, and the wsgi.py. It stands for Web Server Gateway Interface. These are also going to be presented next. In settings.py, we have the settings definitions used by a Django application. This file is referenced by wsgi.py to bootstrap the project loading. In Proj OpenCoast settings.py, we have the definitions of OpenCoast's project. And also it defines the OpenCoast's apps that are further divided into folders in project root, which include the data model app, the front app, wizard app, viewer app, and with app. Also in settings.py, we have the URLs where we imported from the urls.py. And more importantly, we separate the settings.py into two files, a base one, which is static, and a local version for the configuration of OpenCoast's project in that version. The settings_local.py is important by the global version and includes the admin lists, managers' emails, and additional variable settings such as databases, WMS server, and EGI authentication configuration plugin. Regarding urls.py file, we import the urls.py from the OpenCoast apps, which are the data model app, front app, wizard app, and viewer app. Also, it includes the URLs from the admin app. This is going to be discussed next. Finally, in terms of models, we define essentially the database layout with additional metadata. A model is a class that represents a table or a collection in our database. So each attribute of the class represents a field of the table. The models in Django are defined in models.py file inside each app folder. Through this model system, Django provides the ORM support, Object Relational Mapping. It provides a bridge between the data model and the database engine. For the OpenCoast project, we divided the models and hence the database into three apps: the data model app, the front app, and the WIF app. WIF stands for Water Information Forecast Framework. Starting with the data model app, we characterize it as an abstract app because it does not contain views. The data models characterize the deployments that user defined in the front end. This data is added and edited during the configuration steps. Backend does also needs this information to execute accordingly. On the WIF app, it is similar to data model app because it does not contain views. WIF exists as an app in order to support the backend. In fact, WIF app makes the bridge between the executed simulations and the deployments defined by the users. A single model characterized WIF deployments. This table, or model, inherits the data model deployments from the data model app. Regarding the front app, contrary to both previous apps, the front app for the OpenCoast project has also associated views and templates. We will discuss this later. It refers to the overall OpenCoasts website, including actions as login and logout. And in terms of models, the front app includes all models related to the user access to the front end. Also, it includes support models for the proper configuration of a deployment. Here is an example of the models.py file for the data model app, representing a table named model version run period with some fields such as model version and run period. Finally, we present the general overview of the entity relation model for the data model app, separated by configuration-related models and runtime-related models. And on this slide, the entity relation model for the front app, with the same division between the configuration and runtime, but also some of the models that extend the data model app models. Finally, a recap on Django interactions and respective execution steps. A user navigates the website, it triggers a determined URL, the URL dispatcher verifies all included URLs.py URLs, and the app with the triggered URL is issued. And the view action included in the app folder view.py file is ran, and the framework executes the actions in those files. If needed, CRUD actions over models are issued here. Finally, the web browser renders the related template that is placed in the app folder, templates folder. On the third and last part of this presentation, we will discuss the front-end administration. What is a Django admin, and how we can administer OpenCoasts users and groups. Also, the admin actions and history overview, and finally, some examples of the interface of the admin app. So, what is Django Admin? Django Admin is also an app. This app, contrary to the others, it's already distributed with Django package. It is included in the contrib model. The admin app promotes a broad set of features and functions that allow admin users to interact with the Django models from the other apps. It also supports CRUD actions, create, retrieve, update, and delete actions. The admin app is accessible via the site URL /admin. In our case, opencoast.ncg.ingrid.pt/admin. A small notice, only accessible for admin users. Here you have an overview of the admin app interface, where we have first some part related to the groups and users, and additionally we have the models separated by each app. Django Admin is particularly useful for non-technical users that need to enter and edit data. Its interface is easy to use and facilitates simultaneous work from content producers, such as modelers, or the developers. Besides the CRUD actions, it can be also used for data models inspection and data management. As an admin user, one can edit users and groups in a similar fashion as a model. When managing users, there is a set of 3 Boolean flags that characterize whether a user is active, whether the user is part of the staff, therefore allowed to log in to the admin interface, and there's also a super user flag that gives the user the full access to the site and the admin app. Besides the typical user's permissions for creating, editing, and deleting objects, users can also be given permissions through groups. A group is simply a set of permissions to apply to all members of that group. In OPENCOASTS project, only one group has been created so far, a Run3G group. We used it to provide the members of this group deploying capabilities for 3D simulations. Another insight on the admin interface. Here we have different users of OPENCOASTS, and we have three panels. The first panel is just a search over the users. It is on the top left panel. The bottom left panel is the list of the users with some information to describe the users. And the third panel on the right is a filter that allows us to search over the users according to some filters. If we select a user, here we selected Alberto, we have access to its history, some informations according to the register informations, for instance, first name, and also we access the history of actions done to this user. With this slide, we wrap the presentation for front-end concept, implementation, and software overview. If you have any questions, please ask now.
We are now opening a period for questions. If you have any, I'm open. Okay, I think there are no questions. According to the schedule, we are now going for a quick coffee break, 15 minutes. So we'll return at 10:30. Okay, everyone. We are now resuming back the lectures. So we are going to talk about OpenCoast's backend on the next lecture.
Hi everyone, my name is João Rogério and I'm one of the developers of the OpenCoast service, working at LNEC. I'm here today to speak about the OpenCoast backend. In this session, I will begin by discussing some aspects of the backend, what it is, what it's supposed to do, and how. Then I will give you some details about its architecture, where does it fit, and how it is composed. Finally, I will introduce you to the WIF framework, with a brief overview, a simple example, and how it is being used in OpenCoasts. So, what is the OpenCoast backend? In simple terms, it is the simulation engine, a piece of software in charge of providing the predictions. It is represented in the figure by the gray box with the thicker lines. It handles all aspects of the simulation chain established for each forecast. This chain is updated daily. Based on the state of the previous one, new simulations will provide predictions for a period of 48 hours. What does the backend do? For each simulation of all active forecast systems, it executes a sequence of procedures with the end goal of generating the forecast results. For simplicity's sake, the execution may be divided into 3 stages. It starts by preparing the simulation environment. Then it executes the model and finishes by processing the results. A bit more detailed, the first stage resolves things like the folder where to work, looks up for an available hot start file, fetches forcings, creates a log file, etc. The second stage is where the model execution happens, locally or remotely. Finally, the third stage processes the data generated during the model execution. Things like combining hot start and result files, converting files to netcdf format, creating visualization products, compressing big files, and deleting the unnecessary ones, among other stuff. How does the backend accomplish all of that? OpenCoast forecasts use well-established and reliable models, specifically Schism, and in some cases the WaveWatch 3. But a forecast system isn't only the simulation models. There are a lot of logistics that have to be taken care of. That is where WIF comes in, a framework to assist the creation of forecast systems, taking advantage of the learned lessons and the experience gathered with the previous custom-made similar purposed systems in the past 10 years at LNEC. Where does the backend fit into the OpenCoast infrastructure? The backend component is just one piece of the OpenCoast infrastructure. It's represented in the top figure by the darker gray box with thicker lines. While individual, it connects to most of the same components the frontend does, which allows it to work on separate dedicated resources, while at the same time sharing the same state between both. Most OpenCoast components follow a client-server model which facilitates communication between them, even if they are on separate resources. How is the backend composed? It's a Python stack formed by a few packages split into 3 layers represented in the bottom figure. The top layer comprises the OpenCoast specific stuff, including the command line interface tools to interact with the backend. It's implemented as a Django application alongside the other apps used in the front end and sharing the same data model. Then, the middle layer has the generic machinery of the simulation engine used to implement the OpenCoast backend. And finally, the bottom layer includes some other WIF packages for specific tasks, like forcings, to fetch, as the name implies, forcings. and sproxy to offload the model execution to remote resources. The previous slides mentioned several times WIF, which stands for Water Information Forecast Framework. So, what is WIF? In simple terms, it's a Python-based framework that encapsulates reusable components to help build forecast systems without having to start from scratch. WIF is split into several packages, but the main focus here is on the simulation one. This package implements functionality related to the execution of a forecast system through high-level entities. The relevant ones here are series, simulation, and step. Series' main purpose is to build a chain of simulations within a defined interval. Simulation is in charge of executing the steps belonging to it, and step only defines the base of concrete implementations. The top figure shows their relation. Series includes a simulation, and simulation includes one or more steps. These are Python classes, implementing generic behavior, which means they don't provide specific operations for concrete models, like Schism. For concrete model behavior, there are implementations of step, like prepare step or forcing step. The former is concerned with providing the work environment, while the latter fetches the necessary forcings. All of these entities share a common trait, a mechanism to declare their public attributes as a set of inputs and or outputs, represented as bullet points in the figures. Such trait facilitates the communication between them and at the same time allows a good degree of modularity. Now I'm going to show you a simple forecast example using WIF. Now I'm going to show you a simple forecast example using with. Before we begin, let me explain what you are seeing. On the left side of the screen, there's a text editor, where I'm going to show you the example code. On the right side, there's a terminal, where I'm going to execute the code. Okay, let's start with a pretty basic example. In here, I have the implementation of 3 steps. Stage 1, Stage 2, and Stage 3. These are pretty dumb. They just print a sentence. But they will be used as an example to show you what to expect from them when they execute. The function execute is the only thing you will have to implement to create new steps. Down here, each step has one instance. So stage 1 has S1, stage 2 S2, and stage 3 S3. I will execute them one by one using input as a breakpoint between them. So I will have to press enter to continue the execution. So let's see what happens when I execute this example. Okay, so let's ignore the first line, which is internal. The second line is what we were expecting, the only instruction the step has. So S2 will print its sentence, and then S3. So everything works as expected. Now, instead of executing the steps one by one explicitly, we are going to use simulation to do that. Simulation will be responsible for the execution of the steps by the order they are declared. As we can see, the way we declare it is a little bit different compared to before. In the previous example, we created instances of steps and execute them directly. Here, simulation uses templates. These will create instances of steps when they are needed. In this case, simulation is called sim, just like stage 1 is called S1. These names are important, for example, in logging. Steps also got changed. The sentences they print are now a bit more apparent, since we are going to generate more logging. Let's run the example. If we ignore the internal logging, we can see that the output is pretty much the same as before. And the name of the entities are attached to all logs printed, so we know which entity is printing what. Let's make things a bit more interesting. Since we already defined the simulation, why not use it in a series? And that's exactly what we have here. The code barely changes. There's only 2 differences. The first one is that before we were creating an instance of simulation. Now we are creating a template. And before we were running it explicitly. Now we are going to give that responsibility to series. The series is called forecast and is defined with the begin date of today and an interval of 1 day. So let's see what happens when we execute this code. Okay, we can see that the results are almost the same. There's only a few differences. The first one is that now the series creates a simulation with a specific date. And each log record includes the series name in the hierarchies of entities. So in this case we can see that the S3 belongs to sim, which belongs to forecast. Another thing that we can see here is that if we don't define an end date, the series will only launch a simulation for the begin date. So let's define an end date and see what happens. The end date will be tomorrow. Okay, now we already have two simulations. One for today and one for tomorrow. But the steps produce exactly the same result twice. That's because our steps don't use any variable information. They just print a hard-coded sentence. To make these steps useful, we may add input and output attributes to them. These allow any two entities to exchange information. Input attributes consume such information, while output ones produce it. Stage 1 got datetime as an input, and this is only possible because series produces this information. Stage 2 got execution datetime as an output, which will be set to the current date and time. Stage 3 will then consume that information because it declares an attribute or an input attribute with the exactly same name. Let's see what happens when we execute this code. This is the same code as before, only the steps were changed. Okay, we continue to have two simulations in this series, today and tomorrow. But this time around, the steps produce different messages. So in this case, the date time is included in the message. S2 will produce execution date time, which will then be consumed and print by S3 on its message. and the same will happen but for the following day. So S1 will have the simulation date time, while S3 has the execution date time of the S2 of that particular simulation. That's why these timestamps aren't exactly the same. There's a lot more to show you, but this is enough to show what a simple forecast can be using with. Moving on, let's now see how OpenCoasts uses with. The code you are seeing now belongs to the backend launcher, a command line interface tool handling the execution of every simulation in OpenCoasts. There's a lot of code here, but don't worry, we are going to ignore most of it and focus our attention on the things we already know. Before we dive into details, let me just give you a brief overview of the code. On top, we have the typical import declaration. After that, we have the declaration of global variables. Next, there's the definition of a base class, which will be used as the base of the next two classes. In here, it's the class definition for the main WaveWatch 3 simulation. This class is responsible for creating and executing the WaveWatch 3 simulations. Next, we have more or less the same class but for Schism. Meaning, it's responsible for creating and launching the Schism simulations. Next, we have a couple of functions. The first one is for setting up logging, and the second one for the command line interface. And finally, we have the main part. As you could see, we are using classes to encapsulate the behavior of both WaveWatch and Schism forecast systems. This approach makes its usage easier by hiding most of the internal details, since these systems are a bit more complex than the ones from the example before. Here, we just create an instance with some initial values and then call its method launch simulation with a run date. Let's go back to the definition of the WaveWatch class and analyze it for a moment. Focusing on the setup simulation model method, it's here that our with simulation is defined. And since the simulation may be used in a series, it's created as a template. If the simulation template needs to be used outside of a series, it can be rendered and used as a regular instance, like any other template. This time around, the definition of the simulation template isn't so simple. Compared to the example from before, it has a lot more stuff, but at least the structure remains the same. Besides the name and the step templates arguments, there's also step context. The latter is used to pass a list of arguments to all steps, instead of doing it manual for each step template definition. Another novelty is the usage of arguments in step templates. Here, 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 and here. We had already seen a similar usage before, in series, with the begin, interval, and end arguments. The only reason why we didn't see them in steps before, it's because the steps from the example didn't need them. There was always some entity feeding their inputs. Basically, these arguments are another way of passing information to the inputs. Looking at the list of step templates, we can see that it follows a familiar pattern. Prepare, compute, and outputs. Although the first stage being a bit more granular this time, with local workspace, prepare, and forcings. I won't go into detail about the steps, but their names say pretty much what they do. Scrolling down to the Schism class, examining the method with the same name, we can see that the complexity goes up a notch. However, the way of defining the simulation is exactly the same, but with even more steps. The list of steps now also includes the OpenCOAST specific ones, like prepare, update, and finalize, highlighted in yellow. These handle the exchange of information between the web portal and the backends, forwarding all the details about the forecast systems deployed there. Now that we covered everything relevant, let's try the launcher and check what it can do. Since we are dealing with a command line interface tool, let's run it with the --help argument to inform us how it should be used. Before checking the help message, let's look at the information above. It's generated by the shim we are using to provide the necessary environment to run the launcher. Let's ignore the warning and check the help message. The first thing to notice is the lack of positional arguments. There's only optional ones. Besides the help argument, which prints this message, there's only WaveWatch, which only runs the main WaveWatch simulation. Only Schism, the same as before, but for the Schism simulations. Root, to define the root path. If not defined, defaults to the current working directory. Offset, to specify the number of days to offset the run date. It defaults to 0, and the positive numbers means past, and the negative ones means future. Recover, the number of days to recover the simulations. It defaults to 0. Force, to force the recover period even if the heuristic doesn't think that way. Concurrency, to specify the number of concurrent simulations to run at the same time. As proxy, to enable the submission proxy to offload the execution of the simulations, as opposed to run them locally. No wait turns off the wait period before it starts to run. And verbose increases the amount of logging printed to the screen. To end this demonstration, let's run just the Schism simulations, which in this case it's only one quick 2D barotropic system with the increased logging. The whole process for this simulation takes about 5 minutes. While the process continues, let's scroll back to the beginning and check what happened. In this huge wall of text, there are markers that let us know who is doing what. These were already mentioned before, and in this log corresponds to the fourth column of each log entry, which always begins with a timestamp. This entry from the main code tells us the simulation's run date, and this one which deployments are going to run. Then, for each active deployment, a series, in this case called D1 from deployment 1, is created with these initial values. The same goes for the simulation belonging to the series, called schism. It's only when the steps are reached that we start to see some concrete tasks being performed. For example, the first step to execute the local workplace creates the folder where the remaining steps will work. As well as the log file. By the way, the logging of the initial values is a recurring pattern and occurs on every new entity created, usually just before being executed. The second step is the prepare OC. The suffix OC stands for OPENCOASTS and identifies all the OPENCOAST specific steps. This one is in charge of fetching the relevant information about the deployments. This may also include the files submitted and created in the web portal, but only on the first run of each deployment. After that, these files are cached locally and just linked to the workplace. The case here. Something I forgot to mention is that it's also in this step that the deployment run record is created so we can check the simulation state in the admin's web portal. The following step is also a prepare one, but a generic version instead of an OPENCOASTS specific one. Here we can see the setup of the workplace with links being created to the schisms, binary and static folders, trying to find a valid hot start file, found in this case, linking the schism binary and some static files including the hot start, uncompressing the hot start if found and compressed, which it was, and finally the format of the param.in file. The next step is still a prepare one, but only for wave deployments, using Schism's WWM component. In this case, it will simply check the simulation's kinds and continue to the next step. Otherwise, it would run a WaveWatch simulation to produce the necessary forcings and format the WWM inputs.nml file. After all the prepare steps, there's the forcings one. Here, the circulation and atmospheric forcings are fetched. In this case, it's FES 2014 and GFS. In the end, bctides.in file is formatted. At this point, everything is set to run the simulation model. Before the execution starts, the outputs folder is created. And then, the waiting begins for the simulation's end. Meanwhile, there's execution progress reports, including the estimated time to finish, every 5 minutes by checking the mirror.out. After the execution, mirror.out is checked again to confirm the success, or not, of the run. After a successful run, Combine step does the typical procedures of combining the hot start and output files. Additionally, netcdf versions of the outputs are also created. The final generic step is cleanup, which deletes unnecessary files and compresses the ones to archive. And finally, the last two steps and OpenCOAST specific take care of things like publishing the output, hot start, configuration and log files in the web portal, as well as the map layers in the map server, and updating the deployment run record created in the OpenCOAST prepare step. The end. The whole context of execution, that is, all the information exchanged through entities' inputs and outputs during their execution, is at the end of the log. Let's check the workplace folder to see its final state. And that's it. Thanks for your attention. Any questions?
Hello everyone, João Rogério here. I'm sorry for the low resolution. I hope you were able to follow the examples, but don't worry. The source videos for the stream will be shared on the OpenCoast site, which I'm pasting on the chat. But it's opencoasts.lunec.pt. Okay, thank you. I hope you enjoyed.
Welcome everyone, I'm Samuel from LEAP in Portugal, and I'm going to speak on behalf of INCD organization. In this presentation, I'm going to show how EOSCUB provides a better accessibility to existing European infrastructures and services. So what I mean here with infrastructures, well, when someone commonly thinks about infrastructures, the first image that came to memory are conventional facilities such as airports, dams, roads. It's just some examples. But here I'm going to focus on the world of computers and networks. Infrastructures, as the European cloud infrastructures, are digital facilities that comprise hardware, software, and networks at several locations, and it delivers internet technology services to the users within a given community or geographic region. These infrastructures are usually meant to support researchers and engineers in their R&D activities. Well, how can we group all these infrastructures? So we can just think them in the scope, this European scope that are for the international uh, covered projects and also for the country scope. So what are these international wide infrastructure scopes? We have the GM, the GI, and the ODAT and price. Each one is scoped to a specific task. So GM provides the European Academic Network backup. AGI federates compute and data infrastructures, and it is not only in Europe, it extends to the worldwide countries. EUDAT provides data-oriented services, and PRACE that provides access to high-performance computing machines. Uh, in the context of OPENCOASTS, we have two examples of country scoped providers that are INCD and CSIC from Spain, INCD from Portugal, where I belong. Uh, Beside these, there are also another kind of domain-specific infrastructures. They represent uh, more broader integration between the previous domains. So they are built on top of the national and international ones and rely to specific services, such like the WSG from CERN or the LifeWatch, and there is just some examples. So here for OpenCosts, we'll focus on EOSCUB, AGI, and Deodat, and also YANCD and CSIC from the previous presented infrastructures. So what are they? So the EOSCUB is the first entry point portal where end user can access the existing services available from European projects. Then there are, as I presented before, the AGI and the UDAT as the as the layer for exposing the services that exist in all related country infrastructures. Then, as I explained before, we have also INCD and CSIC as the supporters of OpenCOAST project. So let's look into more detail about the front end of EOSCA. So the main point here is to understand what is the vision of this project of EOSCA. So this is like the main point to start using the digital services in Europe. It provides a better way to access and to collaborate and also to share knowledge. The mission is very uh, interesting because it provides a hub as an European level entry for all stakeholders, also cover the life cycle of services from planning to delivery, allows a better interactivity between all uh, participants, and also it is a contact point for researchers and innovators to share and access resources for their R&D activities. So now let's go to look into the infrastructures that are used by OpenCOAST, AGI, and DODAT. So start looking to the data management. There are multiple services. These are some kind of examples of them. So we have the B2 kind of services that are from UDAT, and there is also the AGI Data Hub that is used by OpenCOAST. Also, in terms of computing facilities, we have AGI Compute that allows to run virtual machines, the AGI Throughput Compute that allows to run the batch processing jobs, and also the AGI Container Compute that provides a way to run Docker containers in, for instance, in Kubernetes infrastructures. About storage, there is also a diversity of services like the B2 kind of UDAT services, and also the HGI online storage, and this for store permanent files and also keep metadata for a global scale, but also CERN-VM file systems that allow to distribute software and applications. There is also another kind of services for sharing and discovery, just like you have in normally example as Dropbox, that is B2 Drop here from INCD, or any kind of services that is also there. This is just an example. Maybe the most important one here that solves a very difficult task that I will talk later is about authentication, authorization, and identity. And it is the AGI shaking services that allows to group a multi-federated environment and resolves a problem to connect all the institutions. Now looking to the providers, so I will focus on INCD as an example, what the providers have and can assure to the users. So INCD is a digital infrastructure founded by FCT. It also provides compute and data services, and it collaborates for national and international projects. And as an example, the communities of CERN and F3s as a participation example of projects that we collaborate. We also provide computing services with AGI, such as the clouds, HTC, and the HPC kinds. Uh, it is also scoped to large projects like the CERN and other R&D international projects that we also support here. So for all these kind of infrastructures and all these kind of services, there is a big management requirement. For that, I give here a simple example of our continuous monitoring, that is the with the service nudges. With this, we can review the state of the hosts and also the infrastructures and assure a high quality of the services. Also, with this platform, we can just manage all incidents and give the assurance of a good quality service, and also provides a better way to create probes and analyze all services and try to uh, give a better quality service in the end. All this information are collected from each provider, in this case from INCD and CSIC, and they are collected in a major portal uh, from AGI. This allows for a continuous monitoring and also expose all this information for all the users and to review the availability and the reliability as a way to control and to review the state of the infrastructures. This is an example like the quality of service that you can have in another kind of operators, another private operators, and this also assures a very high quality of services since we can this way connect all the existing infrastructures that collaborate with these projects. So looking to the task of OpenCOAST integration inside EOSCUB. So um, the the goal here was to start from the OpenCOAST code and start using all services that we have with the GI and all infrastructure providers. So for the main services of OpenCOAST, we use the cloud services. For batch processing, we use the AGI, HTC and HPC services. And also for storage, we are using the AGI storage facilities and also the EUDAT and the F compatibility for EUDAT storage facilities also. And for the authentication and integration, we are using AGI check-in. So let's look to the computation part related to the cloud. So the services are being deployed in virtual machines, in cloud infrastructures, adapt previous software release to provide the image to be run in the grid. So these all kind of tasks need to be prepared before these deployments from the existing code, and also extends the scheduler to submit the jobs to the grid. So the idea here is to have all this kind of service and control in the cloud, and then submit the jobs to the grid over these previous prepared services in the cloud. Looking to the grid environment, we use the AGI Workload Manager service that use the DRAC, and DRAC allows to distribute all the jobs between the multiple sites. In this case, we are using two sites that are INCD and IFCA, and with these two sites for getting a way to deploy the software there, we are using UDocker that allows a better integration of software demands into the requirements, the stricter requirements of worker nodes. There is also another task that is related to data transfer, because we need to transfer the data from the cloud to the grid. And for that, we are using the AGI storage services, using more directly the Storm protocol with WebDAV. This allows a better integration in terms of applications, and also provides a good way to integrate the authentication and authorization with AGI check-in services. Also, in terms of data repositories, the solution was synced for also EUDAT. Now is only using AGI storage facilities, but this can also extend since we based on a RESTful API that allows to merge any kind of solution for storage. Looking to the the the, the workload manager, this was a big challenge because um, the client and the integration of software was not so easy at the first step because there are a bunch of dependencies for using Dirac, but this was bypassed using the RESTful API. So using Dirac, as I mentioned before, it is possible to distribute the computing tasks between the multiple sites. It also provides a way to get a better integration and software flexibility for future developments using independent uh, solutions, also with this kind of integration with Dirac service deployments. So in the end, all this platform allows an abstraction to use the multiple solutions of batch systems without regarding to their details. So it can only uh, follow a job description language and submit those jobs into the infrastructures. So what are the benefits of using all these infrastructures as I explained before during this presentation? So as some principal points, I can point here the, the, the access to scientific distributed computing, and also as you can see here the data services tailored to research and engineering, but also to explore capacity and capabilities available at both national and international levels. So this can expand to all resources that exist, not only in Europe, but also worldwide. It also accesses a large portfolio of scientific computing and data services with added value. But the most important topic here is about the authentication and authorization mechanisms, that using AGI check-in, it becomes possible to integrate and to access all these infrastructures with a single point of entry. This also provides a way to all application and services be accessed and controlled and monitored from a single user account. So we can trace all the processes and all the activity from that account and provide a more transparent way to access all these resources and also to do the accountability. There is also another very important topics, such as to provide, since we can reuse all these resources abroad, Europe and worldwide, it becomes a better way to get connectivity and redundancy through the academic networks and resources everywhere. It also provides a way to store, find and share that collections and analysis in the cloud as, as a way to apply the fair data principles and to get these services more visible to all the users and to turn them more feasible for future developments. Also, it is not less important to mention that the interconnect between all this compute and storage capacity with the partners uh, of the project that provides all this platform, and also to create services and portals to explore and share data. So all of these kind of creates a way of liaisons and with merge of knowledge and collaboration. So if you are interested in more details about all these kind of services, you can look to the sites of EOSCUB, AGI, and EUDAT. Thank you for your attention. I will be glad to answer any question. So I hope that I could arouse some curiosity about these European infrastructures and these open projects. I will be glad to answer any question if there is anyone. I'm not listening. Gonçalo, if you just speak, I couldn't listen to you. I only listen noise. Gonçalo, can you try to shake your micro?
Can you hear me?
Yes.
Okay.
Go ahead.
I was saying that Roger did a question, asked the question in the chat. Maybe you can answer, and
Okay.
maybe João, probably.
So the first question I see here is about OpenCoast implements schemes and open source code. And then Roger asks for if there are any plans to make the OpenCoast services a service open source, so other can contribute and or it can be run on other computing infrastructures. Jean, do you want to answer this?
Yes. Hi, Roger. So we are in the process of making our first public release. And yes, to answer your question, we are going to make everything you saw these 3 days publicly available as open source.
So giving some more time for the shy ones that didn't have done the questions yet.
I think João can show the last slide. Oh. And maybe we can ask everyone. We will remain here, so if you have any questions, you can answer it. But just to let you know, so here you have on the presentation slides the link for the evaluation of the course. Please do so. We are quite thankful of your evaluation. So we reached the end of the third day of the second tutorial of OpenCoasts, and it's actually the last day, so we reached the end of the tutorial. We thank you for attending all the lectures. Again, all the lectures are recorded and are available at OpenCoasts site, and that's it. If you have any questions, we are still here for a while, and please send us an email if you're not here on the meeting. Just to try, maybe sound can be better now.
Yeah, it's way better.
Okay, sorry.
So
It
Roger,
was a cable poorly connected. I was saying that please evaluate the course on the link that is provided here in the slide. And I'd like to thank you all for attending all the lectures. We will be here still for any questions for a few minutes. And we end here the last day of the OpenCoasts second tutorial. And thank you for attending. Again, all lectures are recorded, so you can review the whole lectures at opencoasts.ulnec.pt. So we'll be here for any questions.
Okay, everyone, this is the end for the course. Thank you so much for attending, and goodbye.